All right, let's get started. Good morning, everyone, and good afternoon, East Coast. My name is Kevin Sartori. I'm the Product Marketing Manager at 3DR, and it's a pleasure to host you here on the newest 3DR webinar. Today, we're going to talk about how UAVs are changing the surveying industry. One of the most common questions we receive nowadays is around accuracy. How accurate are models, maps, and digital elevation models that are captured by UAVs? How do they compare to traditional methods and to LiDAR? And how ready are UAVs? If they're not already replacing traditional technologies, how can they enhance the toolbox of today's surveyor? To answer those questions, we partnered with one of the leading surveying companies in the country, McKim Creed. It's my pleasure to announce our guest speaker today, Christian Stallings from McKim Creed. Christian is the R&D manager at McKim Creed, and he is a certified photogrammetrist. He holds a master in geographic information technology from Penn State. At McKim Creed, he is responsible for all LiDAR production operations and for the UAV program. This includes training the staff and leading process improvements and quality assurance for data capturing and data processing. Join me in welcoming Christian Stallings. Christian, thank you very much for joining.
Thank you, Kevin. Pleasure to be here.
Perfect. Today, we're going to start by introducing to you McKim Creed. Then Christian is going to explain why and how McKim Creed is using UAVs today. The most important part of the agenda today is 3 real-world client projects that Christian has done this year to evaluate accuracy and cost of UAVs. Finally, we'll conclude with what will happen next on McKim Creed, and we'll leave time at the end for Q&As. So throughout the presentation, if you have any questions, please write them in our chat group. We will collect them and address the most common questions at the end. Perfect. Before I hand over to Christian, I would like to ask a question to our audience. Which surveying methods are you currently using today? Please fill out the poll that should be appearing now on your screen. And please mark all that apply. Perfect. While our audience is answering the question, Christian, I pass it over to you.
Thank you, Kevin. Well, thank you very much for joining us today. I really appreciate the opportunity to talk to you about some of these projects that we've conducted using SiteScan in the R10C. First, a little bit about McKim Creed and what we do. We are a surveying, engineering, and geomatics firm. We were founded in 1978 by Herb McKim and Mike Creed. And we have over 400 employees in 21 offices, and we've completed projects in 38 states and continue to grow that. We can deploy our assets to any region in the United States and beyond, and we've done several projects outside of the United States. So the projects that we're going to talk about today specifically, they were set up because we wanted to assess a couple things. First, we wanted to see the readiness of UAVs to be deployed in certain types of projects. Like many tools, it's not for everything, but for certain things we felt from our testing that we've done over the last couple of years that it could potentially benefit us over some of our other surveying and remote sensing technology. We wanted to evaluate what kind of accuracy we could get and compare that to some more traditional means of data collection. And then kind of determine what's that price model look like compared to some of those different tools that are used traditionally for those specific project sites and any other potential advantages we might have using that technology. And to do that, there was 3 different sites that we collected on this day. To do that, we coordinated with several groups, the city of Wrightsville Beach, the police department of Wrightsville Beach. They helped control the site for us. 3D Robotics, Esri, and the Army Corps of Engineers, and then finally the Audubon Society was there to monitor the birds to make sure that the drone in no way impacted the nesting birds that were there on the south side of Wrightsville Beach as well as the north side of Masonboro Island. So to conduct this, we used site scan with the R10C. The advantages we liked about site scan since we started working with it early on was the ease of use for collecting this information. It's a very simple product to use to design your flights on the fly and modify them as need be. The ability to upload that to the 3DR cloud for processing, and then finally being able to push that information into tools that we use commonly like Autodesk and Esri, or Esri's Drone to Map. So we started using site scan with R10C back in March of this year. However, we've been working with unmanned systems for some time prior to that. We have had a 333 exemption since fairly early on. We were somewhere around 300 on a 333 exemption list. And our focus has always been on trying to make the same kind of products that our clients have always wanted. The end product doesn't change, just the means of collecting that information. So the clients are still going to want the same planimetric information that they've always wanted, held to the same specifications that they've always wanted. Same for the orthophotography, the point clouds that are created through the dense image matching processes, and the surface models, the DTMs, DEMs, if they're brake line and force, and contours. So the products don't change. What changes is the way you collect the information. So you're still held to the same kind of standards. So that's always been our focus, and we felt that the best way to do that is to focus on smaller systems with big sensors to help us achieve the kind of accuracies that our clients expect. So as I mentioned, there's 3 different project areas that we collected on this day. The first one being Wrightsville Beach. This is project 1. And in fact, actually in this image right here, you can see several of the areas that we collected. So we collected from this pier right here down to the end of the island, as well as the inlet jetty for Masonboro Island, which is to the south of that. So the goal for the Wrightsville Beach project was to collect volumetric information for beach renourishment, and we wanted to assess the before and after condition of the beach for any type of storm event. We did this it was a Hurricane Awareness Week, which is kind of salient right now because we have a hurricane coming towards the United States right now. And it's important to be able to know the condition that the beach is in prior to a storm event like this so that reconstruction can take place correctly and you can assess the amount of damage that was done. So the idea is to collect the information, topographical information about the beach before and after a storm event. So to do this, we collected, we laid down traditional ground control. We needed to be able to georeference this information as best we can and to assess it compared to kind of traditional methods. So to do that, we laid down 14 controlled targets. We also went and we collected 22 blind check shots. So it's 2 different types of survey that's done, and this is pretty common with most types of remote sensing projects. You have your targets, your control, which is used to actually reference the information to the real world, and then you have your blind check shots, and these are used to assess the quality of fit of the data. So to do that, we conducted several flights with a few different systems. We did 2 flights with the site scan system with R10C up to the pier, and then we did another flight down on the south side. We also flew the site scan with the GoPro system. We flew that at 400 feet AGL as well because the camera system is a little different. The ground sampling distance obviously is about half that of the site scan system, the R10C system. And then finally, we also flew it with a Phantom 4. We flew that at 200 feet. We flew it a little lower, but we wanted to get a similar ground sampling distance to that of the R10C system. In order to do that, we had to fly it at half the altitude. So this is a summary of the flights from the R10C system from Oceanic Pier down to the Inlet Jetty. As we stated, there's 14 control points. You can see in the photos collected slide that we collected 195 images that covered that area. It took us about an hour, 2 lifts, all told. That includes setup time for each flight. And we got a ground sampling distance of 1.2 inches. So we processed that data. It took about 4.5 hours to produce our orthos, our digital surface models, our point clouds, and our 3D mesh. And then once measured, we were able to calculate our RMSE, which is our root mean square error, and we'll talk about that here in the next slide. So how do we measure accuracy? So again, the idea is to treat this data similarly to that we would data from other systems. So using these processes, we create what some people call dense image matching, some people call it FODAR, structure from motion. It's all the same thing. It's point clouds created from the imagery. And so we wanted to assess the quality of that. And to do so, we treat that the same way we would a LiDAR point cloud. So we bring that point cloud into software that would be used to evaluate that. And in this case, we used LP360, which is an extension of ArcGIS, to verify the quality of the tin. And to do that, we bring in our blind checkpoints and we check the delta between the Z-value of those points versus the Z-value of the tin directly above that point cloud. This is a very common process for assessing any type of point cloud information. So the results, you can see we tested all 3 of those systems that we flew. And if you look at the very bottom, this is the vertical error tested against the point cloud. There's several different things we're looking at down here. You can see our error mean, our error range, our RMSE, and our 95 percentile, which is held to a higher standard. So you can see first the Phantom 4, we had a pretty high RMSE. So it's 0.527 feet, which is pretty high for what we were kind of looking for and the tools we were comparing against. And you can look at the error range on that. So some of those blind checkpoints were hitting anywhere between negative 0.8 feet and positive 1.4 feet. And then if you look at the NSSDA contour interval for that, you can see that the best conceivably do with this data is 2-foot contours. Looking at the GoPro system, you can see that the RMSE is a lot lower. We've got 0.3. Again, a little higher than what we were looking for this type of project, but keep in mind that the ground sampling distance for that was twice that of the R10C system. And the outliers are much lower than that of the Phantom 4 that was flown. And then finally, the R10C system. You can see the RMSE is in the 1300s range. Our error range is much lower. And the minimum contour interval is down to 0.4. So we kind of wanted to know why was there such a significant difference between the Phantom system and then these other 2 systems that we flew, because it didn't entirely make sense. We're using the same ground control, we're using the same overlap, and trying to do the projects as similar as possible towards each other. So we did a little more digging. We used some of the remote sensing tools that we have, and we looked at the distortion plots from those systems. And you can see, first starting with the GoPro in the middle, it's a fisheye lens. It's very, very wide, so there's a lot of distortion in there. And this is typical of what you would expect for this type of camera system. The one that's kind of interesting is the Phantom 4 on the left, where it has all this distortion on one side. And we tried to process this data several times through several different softwares, and we had several folks look at it, and we kept coming up with similar results. We even went a little step further, and we had some friends collect some more Phantom 4 information from different systems, and we kept seeing similar things. And the best we can come up with is possible digital image stabilization going on with the Phantom 4 that might be causing this type of error when doing this type of photogrammetric analysis. The Sony R10C is kind of what we would expect. There's obviously going to be some distortion in the lens, but you can see it's not nearly as significant as any of the other systems. So the next thing we were able to do, fortunately, when we flew Wrightsville Beach, at the same time, the Charleston Army Corps District was planning on doing their terrestrial LiDAR scans of the beach. This was something that they were planning on doing anyway as a pre-storm analysis of the area. So we were very lucky to be able to coordinate with them on this day to be able to collect this information at the same time. They were able to use the same control points that we were using and the same blind checkpoints so we could compare the two data sets. And if you look, you can see that their RMSE was very, very similar to that from R10C. So they're right around 1300s. If you look at the vertical error mean, their vertical error mean was also very similar to ours. However, it happened to be in the opposite direction of the error in the R10C system. So you got kind of the worst case scenario where one data set's a little bit above the control and one data set's a little bit below. So to take that a little bit further, what we wanted to do was do a surface comparison of the two. So we created a bare earth surface of both point clouds. So we were just looking at the bare earth. And again, we wanted to do a delta of the two. So what you're looking at right here are the two overlapping data sets. Areas in green are where there was coincident data and the two data sets were within 3/10 of each other. And areas in purple are where they're either greater than 3/10 or there was not overlapping data. Unfortunately, one of the things with the site scan flight was we weren't able to do it at low tide because of the coordination required with the police department to block off that portion of the beach. So when they did the terrestrial scan, they were able to do it at low tide. So they have a little more data going into towards the ocean than we do. But in general, you can see that the areas where they overlap, they hit very well relative to each other. So the next comparison that we were able to do with this data set, a few weeks before that, some transects were collected of the beach for renourishment programs by New Hanover County. When they do that, they collect those every 1,000 feet and 3 feet down the line. And you can see in the image all those multicolored lines going across. That's all the survey lines that were collected across that. If you look at the bottom of the screen, you can see a profile view of those two data sets. So the red squares are the surveyed points down a profile line, and then the continuous line that goes from green to yellow back to green is the dense image matching data from the R10C system. And you can see they line up very, very well with each other. So the next thing we wanted to do, and in all fairness, this is not what this data is intended for, these profiles, but we kind of wanted to just look at it this way to also kind of show a point, which is traditional survey is going to be more accurate than almost any means of geospatial data collection. But the other factor that you have to consider is what's the density of those points? How well do those points represent all the break lines that exist in an area? So the surface model that you're looking at right here was created with those transects. Directly under those shots, they're very, very accurate, but you can see there's very large areas that you're interpolating. So we ran our blind control points on that, which again is not a very fair assessment, but you can see our RMSE is very, very high. The minimum contour interval for this is 6 feet. And then we did some volume analysis of the black area just to determine the differences between it. And as you can see, it's quite significant between the unmanned system and the surface created from these profile lines. There's a huge amount of variance. So the last thing that we wanted to do is kind of do a business comparison between the unmanned system and some of the traditional methods for this particular site. Now this is specific to this site, so we kind of went through the process of pricing everything each way. Using traditional survey, we're going to have a higher accuracy, obviously, like we talked about in the last slide, so long as we accurately represent that surface. But it's going to be a little more expensive. It's going to take a little more time. The UAS is going to be about 30% cheaper than that. Same thing for the terrestrial scan. The accuracy is going to be comparable, similar to what we're getting with the unmanned system on this particular project. Again, it's going to take a little more time, and there's about a 15% savings with the unmanned system versus the terrestrial system. The aerial LiDAR system is going to be significantly more expensive for this site, and that's important to note. When we talk about using unmanned systems for these type of projects, we're not talking about replacing aerial LiDAR, traditional manned photogrammetry for very, very large projects. What kind of exists right now is a void that the UAS works really well in. When a project's too small, it just doesn't make a lot of sense to use manned aircraft because it's going to take so much to deploy that asset to collect such a small area of information. So for this site, it would have been 60% cheaper to fly the unmanned system than it would traditional aerial LiDAR. And again, that's relative to the size of the AOI. So the next site was the North Masonboro Inlet jetty. This was the barrier island just south of Wrightsville Beach, and it's the northernmost inlet jetty. So when we originally set this project, although this area was controlled, we weren't necessarily planning on flying it. However, the Army Corps of Engineers that was there watching our flights as well was curious if we could fly this jetty. And the reason was because recently they had some work done on it, and they were just curious if they could look at that work. And you can kind of see it in this GIF that's going by. There's some rocks that are pink, and then there's some that are gray. Those pink rocks were recently placed there on that site to kind of repair the jetty. So we went ahead and we flew this. And that's one of the nice things about unmanned system is we have that flexibility to go ahead and plan this on the fly to collect this area. Unfortunately, we did not have any ground control over this area because it was kind of an unplanned flight, and it's a fairly difficult area to collect some targets because it's just a very unsafe place to be walking on. So we covered about 71 acres for that. It took us about 21 minutes total time to fly that. Again, we did not have any ground control. And we had 123 images that covered this area, similar ground sampling distance to what we collected before. So when they had this work done recently, they did have some terrestrial data that was collected of this that we could compare to, which is pretty nice. And you can kind of see in the plan view, or the top-down view that you see on the right-hand side, the white is the terrestrial LiDAR point cloud, and then the colorized point cloud is that came from the site scan system. Again, there was not any ground control, so you can see that there's going to be a little shift. But however, you can see some of the same features similar features between those two data sets. Same at the bottom screen, that's a profile view of the two data sets on top of each other. You can see that shift again. One thing, however, though, that was pretty interesting about this particular project were the orthos. So we gave the orthos to the Army Corps of Engineers, and they were able to look at them and use them, even though they weren't spatially perfect, to assess the work from the subcontractor who had placed the new rocks on the jetty. And they realized that most of the work had done the way it was contracted to do, but they did find areas where things were not 100% how they were supposed to be, and they're able to use that information to go back to the subcontractor and have them make the corrections that were necessary to do it correctly. And there wouldn't have been a practical way to do that otherwise. So it was kind of an unintended benefit of that particular project. So again, kind of a cost comparison for this second site. We didn't do a traditional survey cost analysis. Although it can be done, it is dangerous in a difficult area to collect. The terrestrial LiDAR system that they had collected with, we did a comparison of that. It was about 30% cheaper. And again, the aerial LiDAR, because the site is so small, was about 75% cheaper to do with the unmanned system. So Kevin, I'll pass it back to you.
Perfect. Great. Thank you, Christian. Before we move to the last part of the presentation, to the third project, I would like to take a quick break and ask a question to our audience. What is your top roadblock in using drones in your current surveying job? Take a quick minute to answer. Perfect. Thank you. Thank you very much, everyone. Christian, back to you for the final project.
Thank you, Kevin. So the third site that we flew that day was the Eagle Island disposal site. This is just southwest of Wrightsville Beach, and it's just off the Cape Fear River. And it's a site that is used for dredging the Cape Fear River, for commerce up and down the river. There's a big shipping area just on the north side of Eagle Island. And so what they do is they use these areas to dredge material from the Cape Fear River, and they place it in these holding areas. And they measure it twice when they do that. They measure prior to the dredging effort and then afterwards. And they're able to evaluate how much material was dredged from the river during that dredging cycle. And we wanted to evaluate, could the site scan system collect the same information that was being done with traditional survey, and how did it compare to that? So this is a nadir view of the site. I apologize, I had a little lag there. So what made this site kind of interesting and dangerous was because of all this material that's coming out of the river into these holding areas. You can see this cracked mud right here. Now that's just a thin layer of dried material, but under there it's very unstable and very dangerous to be in. In fact, when they do traditional survey, the way that we were told that they go about it is they take, when they're doing the profile lines across the pond itself, they take 4x8 sheets of plywood and they place them inside there to increase their footprint on the area, and they take their profile shots, and then they take another piece of plywood and they place it in front of it, and they hop onto that one, and they continue across the pond that way, which is not very safe. It's safer than just being on the pond itself, but it's still, you know, you're putting people in harm's way for some potential accidents. So when we went to the site, what we did is we collected part of cell 1 and cell 2, and we did not want to put anyone inside of these areas where they were dangerous. So we collected ground control. We put 7 survey points around the area on the dikes themselves so that we didn't have to go inside of any of these containment areas. And we collected 2 flights, a few more images than before. We collected 214 images over this area. And if we were to, it took about 5 hours to process all that data. If we were to collect the entire cell 1 or cell 2, it would have took about 4 hours to collect the whole area. But for this purpose, we only collected a portion of it to compare. So this is the traditional survey of cell 1. You can see there are about almost 4,000 individual survey shots to collect this area. And you can see how they go about collecting that. They have these lines that go across the pond, and they also have them that go across the dike. And then using that, they're able to reconstruct the surface of that area. So there's about 280 acres in this particular site. And you can see there's some irregularities in the surface. If we zoom in on some of those areas, we can see them in a little more detail. The difficulty when you're doing traditional survey is that you need to be able to interpolate what's going on in the field well, where all those break lines are, so you're efficiently collecting that information to properly represent that surface. And there's some anomalies in this particular data set that we received that are going to show up in the surface model and affect your volume calculations. You can see this right there. So for comparison, this is the UAS data from SiteScan that we collected over the same area. Like I said, it would take about 5 flights to collect the entirety of cell 1, but we did just this small section with 2 15-minute flights. Our point density was about 104 points per square meter. Again, it's a little unfair, but if you did the point average for the survey for this site, it's about 0.07 points per square meter. So as we go in, we look in those areas that we were looking at earlier. These are the same areas, and this is the surface there in the same areas. And obviously, there's a lot more detail in these locations. So the next thing that we want to do is take those survey shots that we had that were collected a little bit earlier in the year and compare it to the surface that we created. Now again, remember we only held 7 control points. We didn't collect any blind check shots for the site because we knew that we had this existing survey to compare to. So what we're looking at, we're using LP360 here again, which is the ArcGIS extension, and we're looking at the surface model created from the site scan system as well as all the survey shots. So we have a plan and profile view again. And if you look at the profile view at the bottom, where you can see where the survey was collected, by and large it was collected really well. All the break lines are collected right where the surface changes on this particular profile line that we have a segment of. You can see inside the pond on the right-hand side of that profile line where there's a difference between the two. That's because these two areas were collected at different times of the year. The traditional survey was collected prior to dredging, and our flight was done after the dredging had occurred for that year. So that's why you're seeing differences on the inside of the pond. But when you look at the dike itself, you can see that the survey and the unmanned, the site scan data line up quite well. So we want to take it a little step further in kind of comparing these two. So similar to what we did with the terrestrial data, we did the same thing with the conventional survey and the site scan data. We took the two surfaces created from each of them and we subtracted them from each other to create a delta, a normalized surface of what is left over. So what you're looking at right there is a surface model of just the difference between those two. And those areas that are green are between 1/10 of a foot and 2/100 of a foot. Inside the pond, like we talked about, it's much higher because material has filled that pond since then. And the other thing that you see is some of the irregularities that were from that particular survey where the two data sets aren't lining up. That's not necessarily an error in the unmanned, the site scan data. It has more to do with the fact that the surface created from the survey had some irregularities in it. But all in all, the two surfaces in the areas where the data hadn't changed lined up quite well. So kind of business analysis of this site, again, similar to what we did with the other two sites. Traditional survey in this particular case is going to be a lot more expensive. It takes about 2 weeks to collect this site, and because of the danger involved and what's required to collect data across that pond, it's a lot more expensive. The UAS was going to be about 80% more cost effective. Similar to the jetty, we didn't price the terrestrial data for this particular one because of the instability of the ground. And finally, the site was a little larger, but it's the same theme with the aerial LiDAR. It has to do with the deployment and the size of the site. The aerial LiDAR would be about, or the UAS would be about 50% cheaper than aerial LiDAR for this particular site. So those were the sites that we were able to kind of assess this with. And we felt like we kind of achieved the goals we were looking for. We felt really blessed that we were able to compare all these different traditional methods of data collection to the unmanned system. And I know it's kind of a cliche, but we felt like, you know, we were able to get it cheaper, faster, and, you know, similar accuracy. And, you know, a fourth circle you could probably add in there is we could collect a lot of this stuff safer for some of these sites, which is a huge advantage. It takes less people for these particular sites to do this. Again, we increase safety, and we were able to create these products quite rapidly as well. So we were pretty excited about that. So as part of this ongoing analysis of unmanned systems and how they work for a geomatic firm like us, you know, kind of the next steps for us, and I'm sure many firms similar to us, is Part 107 is changing things quite a bit. It's simplifying things. We have known rules. We understand how we need to operate in the national airspace and how to do everything under the regulatory system that now exists. So as we go forward as a company, one of the things that's important to us is to get more of our field crews certified and to take the unmanned general, to get their 107 license, standardization of training for safety, for the systems, and creating standards for all of our projects and our systems. So that's kind of our next step right now. You know, we feel comfortable with the technology when it's done properly, and now the process is just to increase the amount of systems that we can have them in more of our areas that we operate to offer more cost-effective, rapid deployment of some of these systems. So eventually we hope to have an unmanned system in all of our trucks. So again, thank you very much for allowing me to tell you about these projects. I really appreciate the opportunity.
Absolutely. Christian, thank you very much for joining. So we'll leave about 10 to 15 minutes for questions. We had many questions coming in. I will just get started with a couple of questions for you, Christian. The first question is, what size of target flags did you use on your control points for a flight at 400 feet?
So it has less to do with the altitude of your flight and more to do with your ground sampling distance. So you want to be able to see your targeted areas well so that you can identify them for when you're doing your bundle adjustment. For this particular project, we were getting around a 1.2 inch ground sampling distance at 400 feet with the R10C system. And the targets we use 16 inch ceramic tiles on both sites. So what we did is we just went to Home Depot, we got these ceramic tiles and we painted them so that they have 4 triangles on them, 2 white triangles and then 2 black triangles all coming together at a point where we can measure the center of that, which is really nice for the beach because obviously when you're working in a sandy area like that, it's difficult to lay down some targets. What we also do typically is we'll lay chevrons on other types of projects. And again, depending on that ground sampling distance, it can vary from 1-foot targets to 4-foot targets.
Perfect. Christian, next question for you as well. So we see the advantage of UAVs because they can capture everything from the air, but we run into some kind of limitation when we have trees and we want to calculate a bare earth model. What is some sort of best practice that you're using to do that?
Yeah, no, that's a great question, actually. So I talked about it briefly. The UAV is not an end-all. It does not replace a lot of things. It's a very tremendous tool used correctly, like any other tool. So what we're doing here, we're doing photogrammetry. We're using a passive sensor. We're reading the light, and we're tying images together. We're doing our bundle adjustment to calculate our external and internal orientations, and then creating this point cloud. To do that, you need to be able to look at targets from more than one angle. You need to triangulate the location to determine that X, Y, Z. And one of the limitations of this particular type of approach is that it does not work well in highly vegetated areas. For these sites that we were doing, we were looking at mostly bare earth areas with not a lot of vegetation. We've found in a lot of research that we've done over the last couple of years that there is a lot of difficulty there, and it is not recommended in a highly vegetated area to try to create a surface model using this particular technique. One thing we're doing to see if we can supplement that a little bit in areas where maybe it's mostly bare earth, but there is some treed areas, is to use traditional stereo compilation to extract some information underneath there. And we're doing a lot of assessment on the quality of fit of the AT solution in those areas right now.
Perfect. And Christian, quick question. When do you say traditional survey, do you refer to a GPS or to a total station?
Both. So we're talking RTK, GPS, VRS, using total stations, just the common tools that we use and equip in our survey trucks. I can tell you for the targets that were laid on these sites, we were using VRS.
Okay, perfect. We had multiple questions coming in asking for what software was used to generate the point clouds. And Christian used the images collected from SiteScan processed through Drone2Map, but the SiteScan license already includes unlimited and automated processing in the cloud. So it can also generate point clouds, 3D meshes, orthos, and contours using SiteScan directly in the cloud. Perfect. Next question for you again, Christian. Do you still need ground control points if you're using a drone equipped with RTK?
Yeah, no, this was a good question. Yes and no. It depends. So there's first kind of what's going on in the background when you're doing a photogrammetric flight. There's two basic components to it, right? We call it your external orientation and internal orientation. We collect a lot of overlapping information, and typically with traditional photogrammetry, both those things are known really well. We use highly precise airborne GPS systems, differential systems, inertial navigation systems that tell us quite accurately what's our orientation, our omega phi kappa, and our XYZ location. And we also are using cameras that have been lab calibrated, so we know those things quite well. When you're talking about a non-metric system like some of these drones, none of those things are known well. If you use the RTK system, your XYZ location for your image can potentially be known well, but your orientation information still is not, because the types of IMUs we're using on a full-scale system are much more precise than the MEMS IMUs that you can fit on these small unmanned systems. So the advantage of an RTK system is when you do your bundle adjustment, you have a known. You have an XYZ known, which when you're doing the bundle adjustment allows you to constrain that tighter to get a better lens calibration. Is it necessary? No. As you can see here, which is using L1 GPSs and proper ground control, you can still get a very accurate point cloud and information from that. The other thing about an RTK system is that your base, if it's not set up correctly, obviously your data can be off. And that's where verifiable accuracy comes in. Much of the things that we do are held to specific standards and require verifiable accuracy. So even, $1.5 million LiDAR system over some project, we're still going to collect ground control because it's not good enough to say that the data meets a standard. We have to be able to prove that it meets a standard. So it requires some type of independent verification. Without that, it's your word against everyone else's. So we feel, because it's been standard in everything that we do in this industry, that it's still important. We need to be able to verify that what you're doing is actually as good as you say it is.
Okay, perfect. We have many questions coming in around equipment, around the camera. So to summarize, the SiteScan unit is equipped with the new Sony R10C camera. We work together with Sony to bring this camera to market. It's a 20 megapixel camera with an APS-C sized sensor, and that's the best camera in the sky for an UAV of that size. It's paired with a professional grade 20 millimeter lens that allows you to take very sharp images. Also, multiple questions coming in around the cost of the system. We encourage you here to visit our website, and under the pricing page, you'll find an overview of SiteScan and what it includes. All right. One of the, on the second question we asked, we saw that one of the main concerns or blockers from using UAVs are drone regulations. And so also multiple questions coming in if you need a license to fly a drone. The FAA made it very easy to fly drones for commercial purposes. The new Part 107 regulations that were announced in August really eliminate all the bureaucratic burden that you needed to go through to fly a drone for your business. Gone are the days where you needed to hire a professional pilot, needed to hire a lawyer, and go through a 4 or 5 months long process to get your exemption. Today with Part 107, you can get flying in just 3 easy steps. First, you need to register your drone. That's a process that takes 5 minutes, and you can do it on the FAA site. The second step is to apply and pass the remote pilot certificate exam. It's an exam that you can take at any FAA site. It's a multiple question exam that takes 2 hours. When you pass that exam, the last step is to apply for a remote pilot certificate, and this is also done directly on the FAA internet site. I think one question for Christian again, like which terrestrial LiDAR system did you use in your project?
That's a good question. I believe it was a Leica scanner. I honestly don't know because we didn't do the terrestrial portion. That was done by the Charleston Army Corps District. But I can certainly find out. Unfortunately, I don't have that right now. But pretty sure it's a Leica system. I also see a question. Someone is asking RTK, IMU. I was kind of throwing around some acronyms that people may not be familiar with. RTK stands for real-time kinematic. And it's a survey approach where 2 systems are used. You have your base and your rover. In this case, the drone would be the rover. And you're kind of sharing satellite information from a known location, from a semi-unknown location to correct for it. IMU is an inertial measurement unit. That's what gives you orientation. There are IMUs in the drone itself. Those are typically what we call MEMS IMUs. What we use on the manned aircraft, the high-end, traditional aerial mapping systems, those are much higher grade IMUs, and they're also much larger. They're the same IMUs that they use in guided missiles, for example, and they're ITAR controlled. I also use INS, it's inertial navigation system. That's just the entirety of all the components in a traditional remote sensing system that's going to give you location and orientation information.
This is more of a business question. How long before you see an ROI when you use a UAV?
Yeah, well, I mean, that's one of the things that you kind of have to, it depends on your individual business model. I can say with traditional tools, they're built to go through quite a bit. When you're talking about like a Trimble R10 system, it's built to be beaten up quite a bit. So for a company like us, we may depreciate that a little bit faster, or excuse me, a little bit slower than we would something like a UAV. We've had, knock on wood, great success with the systems we've had. We haven't had any losses yet, but we also understand that it's just the nature of that type of equipment with so many mechanical parts that the potential loss is higher than some of this other equipment that's heavy and built to take a beating.
All right, Christian, thank you very much for being part of this webinar. I think a couple more information before we close. I encourage you all to visit our website, 3dr.com, to find out more about SiteScan. And if you have any questions, don't hesitate to reach out to us at 3dr.com/contact. Let me remind you, we had a lot of questions coming in on Part 107. We have a practice test and study resources for you to help you practice for the Part 107 test. Those resources are free and are available at 3dr.com/FAA. Just a reminder, we recorded this webinar and we'll be sending out the link to the video to everyone that registered. Thanks again, Christian, for participating.
Thank you for having me.
Perfect, and keep flying. All right, thank you very much.